नमस्कार. जे विद्यार्थी प्रेझेंटेशन करणार असतील तर त्यांनी वन बाय वन इथे प्रेझेंटेशन करायचं आहे. तर जे पेंडिंग आहे त्यांच्यापैकी कोण प्रेझेंट आहे आपल्याकडे आज? आवाज येतोय माझा सगळ्यांना? ते प्रेझेंट करणारे कोण आहेत? सर्वांना आहे का? ठाकूर सोनाली, आपलं प्रेझेंटेशन झालंय का? सोनाली मॅडम जॉईन नाही का? सय्यद मॅडम, आपलं झालंय प्रेझेंटेशन? चॅट बॉक्स मध्ये तुम्ही टाकायचं आहे. ओके. कोण प्रेझेंट करत आहे आता? message आलेला आहे. प्रेझेंट करू शकता. हा नंबर आहे तुमचा लिस्टवर घेण्यासाठी. तुम्ही जे प्रेझेंट करणार आहे त्याने चॅट बॉक्स मध्ये तुमचा नंबर आणि नाव टाकायचं आहे, सो दॅट आय कॅन promote you to panelist and therefore you can present it. तुम्ही नाव टाकायचं आहे चॅट बॉक्स मध्ये, त्याशिवाय समजणार नाही. सोनाली मॅडम, आपण प्रेझेंट करू शकता. तुम्ही तुमची स्क्रीन शेअर करायची आहे.
Okay, sir. Please allow to share my screen.
येस येस येस. तुम्ही स्क्रीन शेअर करू शकता.
Yes, sir.
बाकी सर्व पार्टिसिपंटला सूचना आहे, तुम्ही तुमचं प्रेझेंटेशन जर बाकी असेल तर तुमचं नाव तुम्ही टाकायचं आहे. जर प्रेझेंटेशन बाकी राहिलं तर ते क्रेडिट तुम्हाला तुमच्या रिझल्ट वरती देता येणार नाही आपल्याला. सो एव्हरीवन इज रिक्वेस्टेड टू पोस्ट their names so that we can conduct the presentation. Sonali madam, you can
Ha.
present.
Okay, sir. My screen is visible.
Yes, absolutely visible.
Ha. Okay. Good afternoon, all of you. Myself Sonali Rajendra Thakre, and today I am going to present here my PhD work. The title of my PhD work is High Voltage Solid State Electrolyte for Sustainable Rechargeable Battery Technology. My research guide is Dr. Milind Kulkarni, sir, and my research co-guide is Dr. Nagesh Kupse, sir. My research center is Center for Material for Electronic Technology, CMET, which is found in Pune. Uh, so my talk involves the following contents. Initially, I am going to introduce what is battery, what are the components of battery, then issues in the liquid electrolytes, what are the aims and objectives of my work, and experimental work that I have performed in the laboratory, further physiochemical characterization, future plan, and references. Uh, so all of you know that human beings have required some basic needs like food, water, air, shelter. But in present and future, we must have required two basic needs, which is first one is medicine and second one is energy. So here I am looking for the energy storage device, which is the batteries. These are the historic development of batteries from 18th century to 1996. The first lithium-ion batteries, that is solid polymer electrolyte battery, which is found in 1996. The main research objectives of my work is that to enhance the ionic conductivity of solid polymer electrolyte, enhance electrode electrolyte interface, mechanical stability and flexibility, optimize electrochemical performance, safety enhancement, scalability and commercial viability of battery, and contribution to sustainable energy storage devices. So let's understand why lithium-ion battery. Because lithium-ion battery shows high energy density, fast charging rate, low self-discharge, lightweight, and long lifespan. Let's understand what is battery. Battery is an electric device that converts stored chemical energy into electrical energy. There are mainly two types of battery. First one is primary battery and second is secondary battery. Primary battery means which is also called as non-rechargeable battery. That means the battery which is used for only single times and after using it disposes. So this type of battery are not reused again and again. And this is the major disadvantages of primary batteries. And secondary batteries, the most popular example is the battery which is found in your mobile phones. That means you can recharge this battery again and again and reuse it. Um, the lithium ion battery is the popular example. So to understand the battery, first we know the principle and the mechanism of lithium ion battery. See in this picture, this is the anode and this is the cathode. When battery discharge, the lithium ion can move from anode to cathode, while the charging, the lithium ion can move back from cathode to anode. These are the major components of battery. First one is cathode, anode, electrolyte, separator, and current collector. So what is cathode? Cathode, which is the positive charge electrodes that decide the capacity, voltage, and characteristics of lithium-ion battery. The most popular example of cathode, which is the lithium iron phosphate, nickel manganese cobalt, and lithium cobalt oxides. In traditional battery, the main cathode is LFP, lithium iron phosphate, while the anode is the negative charge terminal. The most popular example of anode, which is found in traditional battery, which is the graphite, hard carbon, and LTU. Then the next important component of battery, which is the electrolytes. Electrolyte that can provide conductive pathway for the movement of ions, that is cation and anion, while charge and discharging. The traditional lithium-ion battery, which is rely on 1 molar LiPF6 salt dissolving a mixture of 1:1 DMC and EC, that is dimethyl carbonate and ethylene carbonate based organic solvent systems. The lithium-ion battery containing lithium, major lithium source salt, which is the LiPF6, lithium hexafluorophosphate, as well as LiTFSI, LiFSI, LiBOB, while the organic solvent system which containing EC, that is ethylene carbonate, DMC, DEC, PC, EMC, and there are so many additives that are added to enhance the performance of battery, such as the VC, vinylene carbonate, FEC, and some thermal stabilizer, which is phosphate-based stabilizers, which enhance the battery performance. So separator is another major components in battery. The function of separator is to prevent the internal short circuit by keeping anode and cathode physically apart, and it allows the lithium ion transport or movement of lithium ion from cathode to anode, and which can enhance the safety of battery. So that I have already told you, the traditional lithium ion battery is based on organic solvents, and due to this organic solvent, some issues are arises in the lithium ion battery. The first major issue is the thermal battery undergo thermal runaway. That means the battery can catch the fires because of this liquid electrolyte. So the my research work is focusing on to replace this liquid electrolyte by using solid polymer electrolytes. This is the literature survey. When I study the literature, this is one major problem found, that is the battery undergo thermal runaway. So let's understand what is thermal runaway. Thermal runaway means when battery undergo charge and discharge, the heat is generated, and because of the organic based liquid electrolyte, some side reactions are happen and the gas are released and the battery become swell and battery catch the fire. This is called thermal runaway. So the my aim is to replace this liquid electrolyte by using solid polymer electrolyte. This is another example. In this slide, I am trying to show one example, the incidents which has happened in the summer in April. See here the Ola electric bike catch the fire due to the thermal runaway of battery. So yeah, what is alternatives for these liquid electrolytes or organic based liquid electrolytes? So the first alternative to use ionic liquids. So what is ionic liquids that I can explain in next slide. Then the second alternative is use gel polymer electrolyte, then solid composite polymer electrolyte, and we also use ceramic glass electrolyte. So my work is focusing on polymer electrolyte. In polymer electrolyte, there are two types. First one is solid polymer electrolyte or gel polymer electrolyte. Solid polymer electrolyte, that means completely solid. There is absence of liquid. While in polymer electrolyte, see in these pictures, gel-like material, that means some liquids electrolyte are present, so that can improve the ionic conductivity. So these are the some common polymer example which is used in our laboratory. First one is PEO, that is polyethylene oxide, polypropylene carbonate, PDAMDMA, PVDF HFP, PVDF. These are the common polymer. So this slide I have already explained. See the picture. This is the solid polymer electrolyte and this is the gel polymer electrolyte. So, why solid polymer electrolyte and what are the advantages of solid polymer electrolyte over liquid electrolyte? So, major disadvantages of liquid electrolyte. First, we have seen that they can catch the fire. Then, second one is they show the poor chemical and physical stability. Then they have an internal shorting, that means leakage of liquid electrolyte. And in case of liquid electrolyte, we required separator for the battery. So if we replace this liquid electrolyte by using solid polymer electrolyte, there are lots of advantages. First one is we have increased the ionic conductivity. There is the no issues of liquid leakage of toxic solvent. Then no extra separator is needed during the fabrication of battery. Then the low flammability, easy to processability, and we can make flexible lithium ion battery. So when I focusing on solid polymer electrolyte, the solid state batteries is arises. So there are some challenges while we fabricate the solid state battery. First is that they have difficult to manufacture due to their solid state nature. Second, to insufficient ionic conductivity. Due to solid nature, they show insufficient or low ionic conductivity. So the challenge is that uh, we have to enhance that ionic conductivity by adding some additives. And third one is poor interfacial contact. That means electrode electrolyte interface contact is poor in case of solid state electrolyte. So we have to focus on to the improve that interfacial contact. So these three challenges in front of me. So to overcome these three challenges, mm, what I am doing, I have take inorganic solid electrolyte mixed with solid polymer electrolyte and prepare a composite solid electrolyte that can improve the ionic conductivity, that can enhance the mechanical strength of our battery, or broaden the electrochemical windows. So in this slide, I am trying to show the advantages of composite solid electrolyte. When we use composite solid electrolyte, the shape of our battery will be flexible. They show good wettability. That means the electrode electrolyte interface issue is solved. They are easy to process. Okay, and uh, non-volatile and no risk of flammability or no risk of solvent leakage, that improve the ionic conductivity and broaden electrochemical window. These are the advantages of composite solid electrolyte. So my work is focusing on to prepare a composite solid polymer electrolyte. For that, I have used aluminum dope lithium lanthanum zirconium oxide material. That is Al dope LLZO. So this LLZO is mixed with starch, PVP, that is polyvinyl pyrrolidone, PVB, BPP, and the slurry is simply prepared by using mortar paster, and this slurry is coated by using Dr. blade on glass plate. The thickness is optimized, and further, uh, this film is peeled out from glass plate and cut into the 18 mm diameter disc shape, calcine this film, and next step is to injection of monomer. Uh, the monomer solution containing ionic liquid. What is ionic liquids, that I explain in next slide. Then ETPTA as a crosslinker and AIBN is the thermal initiator. So this step is known as the in situ polymerization. So when we use in situ polymerization, there is enhanced or good electrode electrolyte contact and fast lithium ion transportation is happen. And so for my case, I use lithium metal as the anode and cathode is a lithium iron phosphate. So this is the optical image or the photographs that I have taken during fabrication. This is the film which is dry or peel out from the glass plate. Further, this film cut into the disc shape separator, and after calcination, before calcination, the film exhibit the pale yellow color due to the some organic residual, and after calcination, these become brighter and more compact or whiten in color. That shows the successful thermal decomposition of polymeric binder and densification of ceramic matrix. So these are the same images for aluminum dope LLZO framework. This is the before polymerization case, and after polymerization or monomer injection. After in situ polymerization, the polymer fulfilled into the this framework, and you are see the difference between before polymerization and after polymerization. Before polymerization, you will see the pore, or after polymerization, it completely fulfilled with the polymers. This is the XRD. This is the pristine aluminum LLZO powder, and this is the framework. These both XRD are completely same. That means they indicates the our garnet type of aluminum LL0 framework maintain as it is after calcination also. So I have told you we are use monomeric solution, and in monomer solution we are use ionic liquids. So what is ionic liquids? Let's understand. Ionic liquids are organic solvent that consist organic cation and polyatomic inorganic anion. It is a salt. They are in liquid state at room temperature. Ionic liquid possesses high electrochemical stability window. There are some examples of cation, imidazolium, pyrrolidium, pyridium, and so on, and inorganic anions like Br minus, Pf6 minus, TFSI anion. This is the monocationic ionic liquids. Most of the research is already done onto the monocationic ionic liquids. And this is the dicatonic ionic liquids. This is the novel ionic liquids that we have synthesis in our lab. So this is the synthesis of ionic liquids. Actually, the synthesis is very simple. This is only SN2 reactions. In step one, only cottonization is happen. We have first take vinyl imidazole and 1 bromobutane at 60 degree. We will get the first step, that is cottonization step. While in second step, we perform the metathesis. Metathesis means uh, the small anion is replaced by a large anion. This is called metathesis, and we will get these ionic liquids. That is, we abbreviated it as VVIM TFSI. Further, I have taken H1 NMR. Uh, in H1 NMR, there are 15 different types of proton. So we get 15 different proton that shows the successful synthesis of 1-butyl 3-vinyl imidazole sodium bromide. So that one term I have already told, in situ polymerization. So during in situ polymerization, in monomeric solution, we have used these ionic liquids, which is act as a monomer due to this vinyl bond. This is the ETPTA, which act as a cross linker. And in this case, I am used thermal initiator, which is AIBN. For the lithium source, I use LiTFSI as a salt, and to enhance the ionic conductivity, I use additive salt, which is LiD4. So see in the photographs, before polymerization, the solution is liquid, and after polymerization, it gets solid in nature. So that indicates the successful polymerizations. So further, I have taken FTIR. The carbon-carbon stretching frequency band at 1660 centimeter inverse, here 1660 centimeter inverse, which is disappear in solid polymer electrolyte. That means they indicates the successful polymerization happen, and the carbon hydrogen stretching vibration at 3155 centimeter inverse, which is for the imidazole ring. Then 740 centimeter inverse, which is the CF stretching vibrations in the ionic liquids. And this is the another vibration peak, which is for the TFSI anion. This is the electrochemical data. How to check ionic conductivity? By using EIS spectroscopy, that is electrochemical impedance spectroscopy, we can optimize the ionic conductivity for our solid polymer electrolyte. For that, I have used LiTFSI as a salt and vary the concentration of LiTFSI from zero point 0.2 molar to zero point 0.7 molars. So I get highest ionic conductivity for zero point 0.7 molars, which is around 1.6 into 10 raised to minus 3 Siemens per centimeters. And further, this solution is used after optimization. This solution is used, and I added a cross-linker into that. Further, ionic conductivity will increases around 1.42 into 10 raised to minus 3 Siemens per centimeter. Here is the graph of ionic conductivity. Further, we have studied the energy of activation by using again EIS. That means at different temperature, we increase the temperature or take ionic conductivity. So as we increase the temperature, ionic conductivity enhance. So in our case, for 55 degrees Celsius, we get 1.42 into 10 raised to minus 3 Siemens per centimeter ionic conductivity. And in this case, the energy activation value is very low, which is around 0.24 electron volt, which is a again indicate which is a very good energy of activation value. Further, we have studied the transference number, and the value of transference number which is around 0.59, and this is the linear sweep voltammetry graph, the electrochemical stability window which is around 5.5 volt. Uh, in liquid electrolyte which is only 4.2. So this is the advantages of solid polymer electrolyte. That means electrochemical stability window value increases. Uh, so finally conclusion. So yeah, in composite solid polymer electrolyte was successfully fabricated, and the ionic conductivity value is around 1.42 into 10 raised to minus 3. Then lithium ion transference number which is 0.59, and electrochemical stability around 5.5 volt. This is the point cell fabrications. Mm. These are the expected outcomes for my work. First one is faster ion transport, enhanced stability, improve mechanical flexibility, enhanced thermal performance, lower interfacial resistance, long-term reliability, efficient ion transport, and scalable and cost-effective production. In future, I'm going to perform physiochemical characterization like TGF, DSC, then further electrochemical studies into that plating, stripping, cycling test for battery. And further, I am going to test half scale, that means battery fabrication, and some morphological characterization like FPSM and post analysis like XPS. These are the references. And finally, I am really thankful to my guide, Dr. Milind Kulkarni sir, my research co-guide, Dr. Nagesh Kupse sir. I also thankful for guidance, Dr. Sudhir Arbus sir, Dr. Bharat Kale sir, and all staff of the CMET Pune. I would like also thank you to Mahatma Gandhi Vidya Mandir, LVS Arts, Science and Commerce College, Panchavati, Nasik, Principal, Vice Principal of LVS College, and also thank you our PhD coursework coordinator, Dr. Satish Ahire sir, and thank you all participants. Thank you so much. Hello.
झाले मॅम प्रेझेंटेशन. कोणाला काही क्वेश्चन असतील तर प्लीज विचारा.
Is there any question? Uh, Hello, ma'am. May I stop sharing?
येस मॅम.
Yes, there is a one question in chat box. Yes, we can replace lithium ion by other metals. In today, sodium ion batteries arises. Then potassium ion battery. So many research is already going on sodium ion battery. Ma'am, EIS, the electrochemical impedance spectroscopy, which is used for how much resistance is in your solid polymer electrolyte or in your system. And with the help of this resistance, we can calculate ionic conductivity for particular solid polymer electrolyte.
Whose presentation is remaining, please raise your hand. Yogita ma'am, are you ready for giving a presentation?
Am I audible, ma'am?
Yes, ma'am, you are audible.
Okay, I'm sharing my screen. My screen is visible, ma'am.
No, ma'am.
Okay, I am trying to sharing. Hello, ma'am.
लॉग आउट झालं थांब थांब
Okay. आता काय करू?
परत ते
My screen is visible, ma'am.
येस मॅम
Okay, I am sharing. I am starting my presentation. Okay, good afternoon, all of you. My name is Yogita Ramdas Thorat. I am my research topic is design and development of composite electrolyte for next generation solid state rechargeable battery. My presentation is my एक मिनिट. My research center is Center for Material for Electronics Technology, CIMET Pune, and my research guide is Dr. Nageshwar D. Khupse, and my research co-guide is Sandesh R. Zadkar. My presentation is going through the following points, that is the introduction, principle of battery, electrodes in battery technology, electrolytes in battery technology, solid polymer electrolytes, experimental, synthetic method, and conclusion. First, we see the what is battery. Battery is a device which converts the stored chemical energy into electric energy. There are mainly four components of battery, that is a cathode, anode, electrolytes, and separator. There are mainly two types of battery, that is a primary battery and secondary battery. Primary battery means which cannot be recharged again and again, that is for only single use, and which can be used again and again. And secondary battery which can be recharged for several times and used for multiple times. For example, lithium ion battery, lead acid battery, and sodium ion battery. Then what is actual principle of battery? The battery works by converting stored chemical energy into electric energy through the oxidation and reduction reaction of electrolytes with metals. This is the actual principle of battery. In this figure, they are showing the how the battery works. That is the positive electron, negative electron, how the movements of the ions in electrolytes takes place, and how the battery is actually works. Next, electrodes in battery. The main components of battery technology is the electrodes. In that, there are the two subdivided components, that is the cathode and anode. First, we see what is cathode. Cathode which decide the capacity, voltage, and characteristics of lithium ion battery. The most favored active cathode materials are oxides of lithium ion, that is the lithium ferrous phosphate, NMC, lithium cobalt oxide. These are the various cathodes which are using in our lab. Then capacity and voltage of lithium ion battery determine the amount of active material loading and potential difference between the cathode and anode. Next, anode. Anodes are these mostly decide the role towards the current to flow through the external circuits. There are different types of the anodes, that is the graphite, hard carbon, yttrium, which supports the reversible shuttling of the lithium ion released from the cathode, and lithium ions are stored in the anode. These are the characteristics features of the cathodes and anode. Next, we see the our main components, that is the electrolytes in battery technology. The electrolytes, which are the conducting substance that allows the movements of ion through the cathode and anode. Uh, Electrolytes consist of the salts, solvent, additive that enhance the conductivity and stability. There are mainly four types of battery electrolytes, that is aqueous electrolytes, organic electrolyte, solid state electrolyte, and polymer electrolyte. The role of the electrolytes in battery technology are which are enhancing the safety, preventing the internal short circuit, maintaining the charge balance, and facilitating the ion movement. These are the two diagrams which are showing the what actually happened with the electrolyte during the charging process and discharging process, how the movements of the electrolyte takes place between the cathode and anode during the charging and discharging. Next, what is a liquid electrolyte and what are the problems in liquid electrolyte? Generally, liquids electrolytes having the relatively high ionic conductivity. It is up to 10 raised to minus 2 to 10 raised to minus 3 Siemens per centimeter, which is relatively high as compared to the other solid state electrolyte. But there are the mainly more disadvantages in liquid electrolyte. The liquid electrolytes are made up from the organic solvents. For example, EC, DC, DMC, and EMC. These are the organic solvents which are used for the preparation of the liquid electrolytes. And generally liquid commercial liquid electrolytes, they are using the LiPF6 as a salt. When LiPF6 is in contact with the atmosphere, there there is a formation of the EHF, that is the hydrofluoric acid, and so the battery get fire immediately. So for the there is these are the disadvantages of the liquid electrolytes. That for the liquid electrolytes, they are needed of separator. They having the poor chemical and electrochemical stability. They having the narrow range of operation temperature, issues of the liquid of toxic solvent. These are the more disadvantages of the liquid electrolyte. So overcome this all the disadvantages, we are using the solid polymer electrolyte. Solid polymer electrolyte having the high lithium ion transference number, high ionic conductivity, wide electrochemical window, good interface contact, low material cost, and enough flexibility. These are the more advantages of the solid polymer electrolyte. So for overcome the disadvantages of the liquid electrolyte, we are focusing on the solid polymer electrolyte. Generally, we are using the ionic liquid-based solid polymer electrolyte. First, what is ionic liquid? Ionic liquids are the organic salt which consist of the organic cations and inorganic anions. They are the salt in liquid state, melting point below arbitrary temperature. They are the largely made up of the ion and short-lived ion pair. Generally, we are using the cations, that is the midazoleum, paryludium, quaternary ammonium-based cations, and anions, that is the bromide, tetrafluoroborate, hexafluorophosphoborate, perchlorate. These are the we are using the anions, but we are preferring the more that is more stable and the useful anions, that is the lithium trifluoromethane sulfonic imides. Then in literature review, we are seeing the what is the advantages of the solid state batteries versus traditional battery. Solid state battery having the higher energy density, quicker charging, potentially safer, reduce weight. Solid state battery can store 2 to 5 times more energy for the same weight. Solid state battery having the potential to be reached full charge in 10 to 15 minutes. They having the lower risk of combustion and remains function at higher temperature. solid state battery can be stacked, or during the battery packaging they can be packed in a single casing, that is can be reduce the weight of the battery up to 30 to 40%. These are the advantages of the solid state battery versus traditional battery. Then we are fabrication method for the for solid state battery in our in we are using the in situ solid state in situ synthesis of polymer electrolyte. First we see the what is ex situ method and in situ method. In previous literature survey they are using a ex situ polymer electrolytes, that is they are prepare the film of solid polymer electrolyte. In this figure these types of fabrication they are taking, but there are the more interface between the anode and cathodes are there. So they are having the major problems of ex situs, that is high interface resistance, low ionic conductivity. To overcome this issue we are using the in situ synthesis of polymer electrolytes, that is the anode and cathode. During in situ polymerization, these interfaces are minimized or fully destroyed, that is enhancing the SEI formation, increasing the ionic conductivity, enhancing the battery performance, improve interfacial contact. These are the advantages of the in situ solid polymer electrolyte. The synthesis methods for preparation of the ionic liquids. We are seeing the synthetic method for preparation of the ionic liquid. Here, there are the mainly two types, two reaction steps are taking place. That is, first one is a simple quaternization reaction, and second one is the metathesis reaction. In quaternization reaction, there is leavage of the chlorine or bromine, that is the anions leavage, and in metathesis reverse replacement of the another anions by first anion. These are the metathesis reaction. Then preparation of the dicationic ionic liquid. First we are seeing the first we are seeing the monocationic ionic liquid, then dicationic ionic liquid. The advantages of the dicationic ionic liquids are high thermal and electrochemical stability as compared to monocationic ionic liquid, low volatility and non-flammability, enhance ionic conductivity, and improve lithium ion transport. These are the advantages of the dicationic ionic liquid. These are some examples of dicationic ionic liquid. Let's going through the one example of solid polymer electrolyte. In that we have taking the 1-vinyl imidazole and the 2-bromoacetophenone. These are the simple SN2 reaction. In that the in that quaternization reaction takes place, and in second step metathesis reaction, that is the bromide ion is replaced by the TFSI ion, and the overall reaction is confirmed by the H1 NMR. These are the synthesis of the ionic liquid. Then this is our schematic synthetic method of ionic liquid and its fabrication procedure. First, preparation of the porous membrane. For the preparation of the porous membrane, we are taking the PVDF, HFP, acetone, and water, and the casting are taking place with the help of the doctor blade, and the slurry are taking at overnight in the oven at the rate 100 degrees Celsius. Hence, these types of the porous membrane we are preparing. And for the preparation of the battery fabrication, we are taking our previous prepared ionic liquid, lithium salt, VC as a cross-linker, and the LiDFOB as the additive. And in situ polymerization takes place during the battery fabrication, and after in situ polymerization, the cross-linking are taking place between the ionic liquid and VC. These types of the in situ fabrication are taking place. Next, morphology of uh, morphology of in situ, morphology of our prepared separator. The prepared separator, FSM images of the prepared separator are given in this slide. Then first A and B, they are showing the porous porous nature. And after the polymerization, the pores are the fully blocks. That is, after polymerization, the solid polymer electrolytes are the blocked in that pores. And in first, the pore size are the ranging from the 1 to 6 micrometer, and which occasionally larger pore size are up to 8 to 10 micrometers. The apparent surface pore opening were significantly reduced to submicron dimension after polymerization. Hence, the polymerization are also taken place, are also confirmed by the FSM images after polymerization. And then characteristics of synthetic solid polymer electrolyte. First, we are taking the H1NMR. First we are taking the IR. In IR, first we are taking the our prepared ionic liquid, which are also consisting of double bond at 1650. We showing the IR peak, and in VC, these are peak are also present at 1650. And after polymerization, these peak are disappear. That means that the polymerization are taken place of double bond. Then in XRD, the crystalline nature of the LiTFSI, we showing the crystalline nature. That is, the peaks are observed in the XRD. And after we are missing the LiTFSI in our ionic liquid, these peaks are disappear. That means LiTFSI is fully miscible in our ionic liquid, and which shows the amorphous nature. If more the amorphous nature, more the ionic conductivity. Hence, these are the useful for our battery fabrication. Then these are in third figure, that is a C. This is the TGA. The in TGA, PVDF HFP after polymerization is most thermally stable, followed by the our ionic liquid polymer, and then pristine PVDF HFP is least stable. That is, after polymerization, our separator is become a more thermally stable. And this in D, we are taking the stress strain study. That is, the first we are taking the stress strain study of our prepared PVDF HFP, and then after polymerization. In that prepared PVDF HFP, we showing the linear elastic stability up to 8.43 millipascal, and then after polymerization it shows up to 12.33 millipascal, means which is the more stable as compared to the prepared PVDF HFP porous membrane. Then electrochemical characterization of solid polymer electrolyte. First, which is the uh, first is the Arrhenius plot. In that, we are taking the EIS of our EIS of our solid polymer electrolyte from 25 degree to 70 degrees Celsius. In that, if temperature is increases, ionic conductivity is increases, and the energy of activation is determined up to 19.91 kilojoule per mole, which is the best. And then we are taking the LSV, that is a linear sweep voltammetry in figure B, which is up to a 4.8. In a traditional electrolyte, it is up to, or in generally liquid electrolyte, it is up to 4.2, and in our case, it is reach up to 4.8 volt. It is a same as compared to the solid polymer electrolyte. Then third, we are taking the transference number. The transference number which are up to the 4.52, which is relatively same to the typical polymer electrolyte. And then D, which indicates the reversible plating stripping process of the solid polymer electrolyte. These are some electrochemical characteristics of the our prepared solid polymer electrolyte. And then battery performance of synthetic solid polymer electrolyte. In that, we are taking the rate capability performance from the 0.05 C to 1 C. That is the in first figure, we are taking a rate capability test from the 0.05 C to 1 C. They are taking, and in figure B, they are the charge discharge profiles of the real IPF4 to lithium cell. Here we are using the lithium as a anode and the LiPo4 as a cathode. Then we are taking the cycling performance of our solid polymer electrolyte up to 1000 cycle. Here is the Coulombic efficiency is up to 99.5%, which is the best and which can be then D in figure D. There is a chart discharge cycling performance at 1C. Hence, these are at first cycle, 400 cycle, 800 cycle, and 1000 cycle. These are the cycling performance of the our synthetic battery. Then we are also taking the cyclic performance of the synthesis solid polymer electrolyte at 0.05 C, which is also stable up to a 50 cycle. So these are the this showing the good battery performance of our synthetic solid polymer electrolyte. The conclusion of our work in that we are synthesis the successful polyionic liquid solid polymer electrolyte via in situ thermal polymerization of ionic liquid, that is we are abbreviated as VBEAM TFSI using VC as a crosslinker. The ionic conductivity was found to be highly dependent on lithium salt concentration. In that we have also taking the ionic conductivity of different lithium salt concentration from 0.2 to 1 molar. In that we have getting the highest ionic conductivity at 0.7 molar, which having delivering the highest optimal performance. Then the resulting polyionic liquid solid polymer electrolyte exhibiting the higher ionic conductivity, that is a 4.0 into 10 raised to minus 4 Siemens per centimeter inverse at 30 degrees Celsius, and we showing the high electrochemical stability window up to 4.8 volt and high lithium ion transference number, that is the 0.52. Moreover, the lithium symmetric cell demonstrate a stable plating stripping for 1000 hour at 0.1 milliampere per centimeter raised to minus 2, and our battery performance are showing at 1C for 1000 cycle with discharge capacity 100 milliampere hour per gram inverse, and the extreme extending Coulombic efficiency up to 99.5%. Looking ahead, this strategy could be extended to other alkali metals, that is the sodium, potassium, which can be providing a new opportunity for the development of durable, high performance solid state batteries based on in situ polymerized ionic liquid electrolytes. Then the expected outcomes, that is faster ion transfer, enhanced stability, improved mechanical flexibility, enhanced thermal performance, lower interfacial resistance, long thermal reliability, efficient ion transport, and scalable and the cost effective production. That is, we are expecting that the lithium ion transport should be faster as compared to our traditional electrolytes. Thank you, all of you. Am I audible?
Yes, sir.
If anyone has question, then please ask. Can I stop sharing my screen, ma'am? Okay, there is some question, I think. Can I stop sharing my screen, ma'am?
Yes, ma'am.
Okay, thank you, ma'am. There is one question that is what is current efficiency of एक minute. What is current efficiency of this battery? We are taking a performance of our solid polymer electrolyte with the help of the LFP, that is a lithium ferrous phosphate as a cathode and lithium as anode. We are testing it for 1C and which are delivering up to 1000 cycle and which showing the up to the 99.5% efficiency.
Pradeep sir, you can start your presentation.
Ma'am, my screen is visible, ma'am. Hello.
Yes, sir. Yes, your screen is visible.
Okay, ma'am. Can I start my presentation, ma'am?
Yes, sir, you can start.
Okay. Good afternoon, everyone. I am Mr. Pradeep Rajaram Dhanavade, research student at CIMET Pune, working under the guidance of Dr. Nageshwar Kupse sir, and my co-guide is Dr. Ramachandra Kalubarni sir. Today I am presenting my research work titled Development of a Deep Eutectic Solvent as an Electrolyte for Sustainable Lithium-ion Battery Technology. This work focuses on developing eco-friendly, safe, and efficient electrolyte for a next-generation lithium-ion battery. Lithium-ion batteries are the backbone of modern electronics, electric vehicles, and renewable energy storage system. Uh, because thanks to their high energy density and long cycle life. However, their performance largely depend on the quality of the electrolyte used. Traditionally, these batteries are organic solvents that are flammable, toxic, and environmentally hazardous. This brings us to the need for a safer and greener alternatives. Electrolyte facilitate lithium-ion movement between the anode and cathode, essentially for the current generation and overall performance. So, developing a better electrolytes is a key area of research. Mainly, there are. I am introducing you the what are the Ds. Deputic solvents. Ds are ionic liquids formed by the combining a hydrogen bond donor, which are acronyms as HBD, and hydrogen bond acceptor HB. These combination result in a room temperature stable solvents that are non-volatile, biodegradable, and tunable. What makes these so exciting in their alignment with the green chemistry principles? They are easy to prepare, eco-friendly, and can potentially replace hazardous organic solvents in lithium-ion batteries. So this is some example of HB and HBDs. In left hand side, we see the some quaternary ammonium cations like chlorine chloride, choline chloride, acetylcholine, and betaine. And in right hand side, some different examples of hydrogen bond donors like amino acids, diols, amines, organic acids, sugars, polyols. This is my literature review. In my literature review, we identify the various enhancement strategies like composition and tuning of HBDs and HBAs, forming hybrid electrolytes with the polymer on or ionic liquids, using additive to reduce viscosity, designing a smart material like self-healing or fire resistance to gels. There are the different types of Ds. Mainly, they are categorized in five different types, which is from metal halide base to phenolic types have been tested, but each has a limitation like a narrow electrochemical window or a high hygroscopicity. Also, in a literature review, there are some work has been published like Mariam Anotti et al. Using a system like N-methyl acetamide with LiTFSI, which is showing a very good high ionic conductivity, which is 28.4 millisiemens per second at 150 degrees Celsius. Also, there are some examples which I have taken for referencing. So there are research problem which have find out, despite the potential of Ds, there are some significant challenges that my research addresses. Their ionic conductivity is relatively low. They tend to absorb moisture due to their hygroscopic nature. High viscosity hamper lithium ion mobility. Many Ds show poor thermal stability and are hard to recycle. Also, very few studies have systematically optimized the HBD-HBA combination for battery applications. Hence, there are a clear gap in exploring DS composition tailored for high performance electrolytes. There are the motivation, which is these possess a number of desirable traits. They are safe, biodegradable, cost effective, and electrochemically stable. They have tunable physical properties like viscosity and conductivity, and they are compatible with different electrode material. All of these makes them highly suitable for developing a sustainable battery technology. There are objective. The key objective of my work includes synthesizing and characterizing DES-based electrolyte with improved conductivity and stability, studying their viscosity, ion mobility, and thermal behavior, evaluating their performance in a lithium-ion cell, exploring low temperature and humidity affect their performance, using additive and non-structure to optimize these formulations. For the synthesizing the diphthitic solvent, we use a different. There are different methodologies like heating, evaporating, grinding, ball milling, freeze drying, hot melt extrusion. but heating method is a very simple method and widely used method, so we go through that. And there are the synthesis. D is using various SBD combinations, physicochemical characterizations through techniques like FTR, DSC, and viscosity measurement, electrochemical testing using a CV, EIS, and other techniques, battery cell fabrication with the coin cell to test practical performance, data analysis to correlate the structure property performance relation. These methods allow through the evaluation of DS performance. Uh, there are some expected outcomes we aim to achieve: safer, non-flammable, and green electrolytes, improved conductivity in the range of 10 raised to minus 3 Siemens per centimeter, better correlations between the chemical structure and physical properties, electrochemical windows greater than 3.5 volt, and high Coulombic efficiency, compatibility with electrodes and flexible battery systems, guidelines for designing next-gen DS electrolyte. There are a significance of my study. This work support the global push for a safer, sustainable energy solution by replacing toxic organic electrolytes with DEs. We reduce environmental hazards while enhancing battery safety and performance. The finding can influence both academia and industry, especially in developing solid state and flexible lithium ion batteries. These are which have I am using references to study. Also, a detailed list of scholarly referencing support the research, spanning key journal like Electrochemical Acta, J Power Sources, and ACS Energy Letters. Thank you to I would like to thank to the Director General of CIMIT, Dr. Milind Kulkarni, my guide Dr. Nageshwar Kupse sir, co-guide Dr. Ramchandra Kalugarme sir, and MG Nete Venkatrao Hire College, Nashik principal, and coordinator of this PhD work, Dr. Satish Ahire sir. With this, I conclude my presentation. My vision is to contribute to the cleaner and safer tomorrow through the sustainable battery technology. I look forward to your valuable feedback and suggestion. Thank you. If any question, please ask.
Presentation झालं sir. You covered many aspects related to your topic.
Hello, sir. I am not hearable, sir.
Presentation म्हटलं.
सर आवाज क्रॅक होतो. ऐकू येत ना सर मला काही.
जर कोणाला काही क्वेश्चन असेल, काही क्वेरीज असतील तर तुम्ही चॅट बॉक्स मध्ये टाकू शकता.
Can I stop my presentation, sir?
Yes, yes, absolutely. जर कोणाला काहीच क्वेश्चन नसेल आणि आजचे प्रेझेंटेशन आपले कव्हर झालेले आहे, तर उद्या परत एकदा आपण प्रेझेंटेशन सहित भेटूयात. आणि सर्व पार्टिसिपंट ज्यांनी आज प्रेझेंटेशन दिले ते छान प्रेझेंटेशन होते. सर्वांना डिपार्टमेंट ऑफ केमिस्ट्री कडून चांगल्या रिसर्च साठी शुभेच्छा. आणि आपण इथे थांबूयात. तुम्ही एक्झिट झाले सर्व तरी चालेल.
Thank you, sir. Thank you very much.